In 2019, Google announced that its 53-qubit quantum processor, called Sycamore, had completed a specific calculation in 200 seconds. That same calculation, they said, would take the world's most powerful classical supercomputer 10,000 years. IBM disputed the claim within days, saying their own machines could do it in 2.5 days. Both numbers are staggering. But buried inside that argument was a question almost nobody asked out loud. What is a quantum computer actually doing that a regular computer cannot? Not the marketing version. The real physics. That is what this is about. Here is why the answer matters more urgently than most people realize. Every major bank, intelligence agency, and technology company on Earth currently protects its data using encryption built on a simple mathematical fact. Classical computers cannot factor enormous numbers quickly enough to crack the code. RSA encryption, which shields your bank login, your medical records, and most financial transactions globally, depends entirely on that limitation remaining true. A sufficiently powerful quantum computer breaks RSA encryption the way a key breaks a lock. The National Institute of Standards and Technology finalized its first post-quantum encryption standards in August 2024, explicitly because they believe quantum machines capable of breaking current encryption could exist within a decade. That is not a distant theoretical problem. Governments are already re-encrypting classified archives today because data stolen now can be decrypted later once the machines exist. Your financial history, your communications, your identity data, all of it is being quietly assessed for vulnerability right now. To understand why quantum computers are genuinely different, you need to understand what a classical computer actually is at its core. Every calculation your phone, laptop, or server performs comes down to transistors, tiny switches that are either on or off, representing a 1 or a 0. That binary digit is called a bit. A modern processor contains over 100 billion of these transistors, switching states billions of times per second. The entire history of computing, from ENIAC in 1945 filling an entire room, to the chip inside your watch, has been about cramming more of these switches into smaller spaces and making them toggle faster. It is an engineering achievement of almost incomprehensible scale, but the fundamental logic has never changed. Every piece of information is a 1 or a 0. Every calculation is a sequence of those choices. That architecture is extraordinarily powerful for most tasks. But for certain classes of problems, particularly ones involving searching through vast numbers of possible solutions simultaneously, it runs into a hard wall. Quantum computing does not improve on that architecture. It replaces the architecture entirely. The first thing most explanations get wrong is this. A qubit is not simply a bit that can be both 1 and 0 at the same time. That description sounds impressive, but it tells you nothing useful. Here is what is actually happening. A qubit is typically a physical object, sometimes a superconducting circuit cooled to 15 millikelvin, which is colder than outer space, sometimes a single trapped ion held in place by magnetic fields. At that scale, quantum mechanics governs the object's behavior. One of quantum mechanics' core properties is superposition. The qubit exists in a mathematical combination of states, described by probability amplitudes, until you measure it. Think of it less like a coin that is simultaneously heads and tails, and more like a spinning coin. While it spins, it has a probability of landing on either face. The moment you look, it chooses. But here is the critical part that changes everything. Before you measure it, you can manipulate those probability amplitudes with extraordinary precision using microwave pulses or laser light. You are not guessing what the coin will do. You are tilting the coin before it lands. That ability to engineer probability before measurement is where quantum computing's power actually lives. Now here is the revelation that genuinely overturns how most people picture this technology. A single qubit in superposition is not impressive. The power emerges from entanglement, and the numbers become almost hallucinatory. When two qubits are entangled, the state of one is instantaneously correlated with the state of the other, regardless of physical distance. Einstein called this spooky action at a distance, and he hated it. But it is real, experimentally confirmed thousands of times. When you entangle 300 qubits together, the system can represent 2 to the power of 300 states simultaneously. That number, 2 to the 300, is larger than the estimated number of atoms in the observable universe. A classical computer exploring those states one at a time would need more time than the universe has existed. The entangled quantum system holds all of them at once as a single coherent mathematical object. Google's Sycamore had 53 qubits. IBM's Osprey processor, released in 2022, had 433. IBM's Condor chip crossed 1,000 qubits in late 2023. The raw qubit count is climbing exponentially. But raw qubits are not the whole story, and this is where the honest complexity begins. What makes a quantum computation actually work is a third quantum property called interference. Here is the mechanism. Once you have your qubits entangled and in superposition, encoding the problem, you apply a sequence of quantum logic gates, operations that rotate the probability amplitudes of your qubits. The goal is to design these gate sequences so that paths leading to wrong answers destructively interfere with each other, like two waves canceling out, while paths leading to correct answers constructively interfere, amplifying their probability. Think of it like noise-canceling headphones, but for wrong answers. When the calculation is done and you measure the qubits, the system collapses to a definite state, and you read out an answer. Because of the interference, that answer is overwhelmingly likely to be correct. You are not exploring every solution one by one. You are sculpting the probability landscape of the entire solution space simultaneously, then harvesting the peak. The counterintuitive part is that this process works even though you never directly examine the wrong answers. They cancel themselves out mathematically before you ever look. This is why quantum algorithms are genuinely hard to design. You have to engineer the interference pattern precisely, and that requires deep mathematical insight into the structure of your specific problem. The honest complications are severe, and the industry does not always advertise them clearly. The first is decoherence. Qubits are extraordinarily fragile. Any interaction with the environment, a stray electromagnetic field, a vibration, even a cosmic ray passing through, collapses superposition prematurely, destroying the calculation. This is why quantum processors must operate at temperatures colder than deep space, inside shielding that costs millions of dollars. IBM's current error rate per 2-qubit gate is approximately 0.1 to 0.3%. That sounds small until you realize a useful quantum algorithm may require millions of gate operations. Errors compound. The second complication is the quantum advantage gap. Most practical problems do not yet have quantum algorithms proven to outperform classical computers. Quantum advantage is real for specific cryptography-related tasks and certain simulation problems in chemistry and materials science. For general-purpose computing, classical machines still dominate entirely. The competition is not over. Microsoft, Google, IBM, and a dozen well-funded startups are all racing toward what researchers call fault-tolerant quantum computing, which requires error-correcting codes that need roughly 1,000 physical qubits to produce a single reliable logical qubit. That math means a practically useful machine may need millions of physical qubits. What this means for your life is specific and near-term. If you work in cybersecurity, pharmaceutical research, financial modeling, or logistics optimization, the timeline you need to watch is 2030 to 2035. That window is when multiple research teams predict fault-tolerant quantum machines capable of running Shor's algorithm at scale, the algorithm that breaks encryption. Companies like Quantinuum, IonQ, and PsiQuantum are publicly targeting that range. If your organization handles sensitive data and has not begun migrating toward post-quantum cryptographic standards, that is a vulnerability being created today. For drug discovery, quantum simulation of molecular interactions could compress a decade of lab work into months. Pharmaceutical companies, including Roche and Pfizer, have active quantum computing research partnerships right now. If you work in materials science or battery technology, quantum chemistry simulation may solve problems in superconductivity and energy storage that classical computers have hit hard walls on. The disruption will not arrive everywhere at once. It will arrive in specific sectors, on a specific schedule, and the organizations watching closely will have a years-long head start. What you have just understood is something that took